Hi girls, today's lesson is about weight and weightlessness. It is the last part in our section 3, motion in space. First, weight, you all know it. It is the force exerted by gravity on our bodies, which is equal to the mass of our body times g, which is the free fall acceleration, or we can call it the acceleration due to gravity, which is 9.81 meters per second squared. Specifically, the weight of something is the force that is exerted against the supporting floor or weighing scale. Okay, now we will start with a new concept. So before we talk about weightlessness, we will talk about a bathroom scale that you all know it. We usually stand on our bathroom scale in order to measure our weight. Okay, so if you are standing alone on the scale, the scale will measure your weight. Okay, but if, for example, your friend comes and pushes down on you, you will notice that the reading gets higher, right? So why? Because the scale now is measuring your weight plus the force applied by your friend. Okay, so we can say that here the scale is measuring all the downward force, okay? And because girls, that according to Newton's third law, we know that if you exert a force on another thing, here you are exerting force on the scale in its turn will exert an upward force on you. Okay, an equal and opposite force. So an upward force on you, this is called contact force, or Fn. You remember it, normal force. It is the force exerted by the surface on an object placed on it. Okay, so the scale measures the downward force exerted on it, and this downward force exerted on it, according to Newton's third law, it's equal to the force exerted by the scale on our body. So conclusion, the scale reads the normal force acting on you. The scale reads the normal force acting on you. What is the normal force? It is the force exerted by the scale on your body. Okay, so again, the reading will change if someone pushes down on you, as I told you, so the reading will get higher. If, for example, like here in this picture, lift up on you, also the reading will change. If you stand with one foot on the scale and you lift one foot, also the reading will change. But however, girls, your weight hasn't changed. So here the readings in these positions change, but my actual weight, my true weight, hasn't changed. So what is the scale reading? The scale is reading the normal force acting on you, the force exerted by the scale on us. Okay, this is the first rule. You have to put it in your mind. So always the scale that we stand on, it measures the upward force exerted on our body, the normal, we call it the normal force. Okay, weightlessness, what is this concept? From the word itself, it means that you are feeling weightlessness, like you are feeling that you have no weight. Okay, so this weightlessness occurs when there is no force of support on your body. Nothing is supporting your body. Okay, when your body is effectively in free fall, accelerating downward at the acceleration of gravity. Now you might not get this sentence, but now you will get it when I explain using the elevator example. So stay with me. I will use elevator example. We are going to talk about each one of these cases. When you are in an elevator at rest, here you will feel your true weight. We will explain it. And when the elevator goes up, you will feel heavier, yourself heavier than the true weight. and when the elevator goes down you will feel yourself lighter, okay? And when the elevator, for example, cable breaks, you will feel that you have no weight. You are experiencing weightlessness. Okay. Case number 1. No acceleration of elevator. What means no acceleration? Acceleration equals 0. It means what? No changing in speed. It means, girls, the elevator may be at rest. So if the acceleration of the elevator is 0, then there are two possible scenarios. What are they? Maybe the elevator is at rest, so stationary. When stationary, it means, girls, no motion, no velocity, so for sure acceleration equal to 0, right? Or maybe the elevator is moving, but moving, with constant speed. The speed is not changing, okay? So, and we know that acceleration is equal 0 when the velocity is not changing, because acceleration is the change in velocity. Okay, we took this before in the equilibrium part. Okay, so no acceleration, maybe the elevator at rest, maybe the elevator is moving with constant velocity. Okay, in this case, let's see. In this case, I have two forces. What are they? I have the weight of the person, the true weight, which is the force exerted by Earth on the person. Here, our example, the person is 50 kilogram. Okay, therefore, its Fg is equal to what? Mg, right? M times G. And what is M? 50. And what is G? It's 9.81. We can approximate it to 10. So 500 Newton, okay? So 500 Newton. And since here the person is in equilibrium, so the upward force by scale, see? Force by scale. It means the force exerted by scale on your body. We call it Fn, normal, Fn. Okay, in this case, if we use, girls, a Newton's second law, you remember it? Sum of forces is equal to ma. What are the forces here? If I want to get the sum of forces, they are two. Fn, I take it positive because it's upward in the positive direction, and Fg, okay, I will take it what? Negative, because it's in the downward direction. Equals to what? Since here the object is not accelerating, so A0, so here what? 0. Remember? In case what? In case no acceleration, so F net is what? Is 0. Okay, in this case you bring Fg to the other side, and Fn is equal to Fg. And here we care about what? Fn, because this is the reading of our scale. This is the reading of our scale. So the person pushes down on the scale with force of gravity, which is negative mg, negative 500, and the scale pushes back against the man with normal force equals plus mg. So here, so what is the reading on the scale? We care about the reading. The reading here is the same as Fg. It is 500. Okay, why? Because our elevator at rest, and even if the elevator is moving with constant velocity, the answer would be the same. This is case number 1. Now, case number 2. You are in the elevator and the elevator is going up, is accelerating, is speed. What means speeding up? The velocity is increasing, the velocity is changing. It means there is acceleration. Okay, there is acceleration. So what are the forces again together? Yalla, girls. So here the scale has to push upwards with extra force on the person to accelerate the person mass up. This results in what? In a greater contact force between the scale and the person. Therefore, the normal force is larger. We will prove this together. See, we have two forces here, Fn and what? Fg. Fg, it's known. What is it? It is just the mass of the person, which is fixed, 50 kilogram, times g. So it's always what? 500 Newton. So the weight, the true weight, hasn't changed. It is the same. Okay? But the reading on the scale is changing. So the reading of the scale, it doesn't give you always your true weight. It gives the apparent weight. Okay, let's see. So here you have two forces, and see they are saying, girls, that the acceleration is 2 meters per second squared upward. The elevator is moving upward. Let's only apply Newton's second law. Sum of forces is equal to ma. What are the sum of force? What is the sum of forces? Is negative Fg, because it's down, plus Fn, okay, I wrote it here as n only, equals ma. So tell me here, acceleration isn't a vector quantity? It is. So for sure here we have to take into consideration what? The sign of acceleration. What do you expect? What is the sign of acceleration? Is it positive or negative? Yes, it's positive. Why? Because the elevator is accelerating upward and speeding what? Up. Here we're saying that it's speeding up. When an object speeds up, what does this mean? It means that the acceleration is positive. Okay, so I will just keep it ma. Okay, so what do we care about? We care about Fn, because this is the reading of the scale. This is the reading of the scale. Fn, what is it? If you bring Fg to the other side, it will be positive, right? So Fg plus ma. What is Fg, girls? It's 500, right? 500. Okay, and what is ma? The mass of the person is 50, and we're saying that the acceleration is given as 2. So 50 times 2 is what? 100, right? So plus 100. So 500 plus 100 is 60. So what are you going to read on the scale below you? You are going to read 600 Newton. So you are going to read a number which is greater than your true weight. Your true weight, what is it? Is 500. And you are going to read what? 600. Because Fn, okay, the force exerted by the scale on you is 600. Okay, here the explanation of this case. Now, the third case, you are going down and the elevator is speeding up. Okay? Okay, so here the acceleration also the same. Let's say that you are going down with acceleration of 2 meters per second squared. If we apply the same thing, if we say that's a sum of forces ma, can we cancel a here? No. Okay, what is the sum of forces? We have only two forces, Fg and Fn, right? Fg, okay, Fg, it is the force, gravitational force exerted by Earth on you, which is always the same, is 500 Newton. Okay, 500 Newton. Okay, so let's apply this one. The overall acceleration of the person is downward. So ma, what do you think? Acceleration here is positive or negative, since the elevator is moving down in the negative direction, right? So a here is negative. So when I use this equation, I will put here negative ma. Negative ma. Okay. Number 2. The only external forces are two. What are they? Acting on the person are the force of gravity, which is also acting how? Down. So negative mg, negative fg, which is equal to negative mg, and the supporting normal force. What is the supporting normal force? That the scale applies. The scale applies. So this is the force exerted by scale on you. This is the normal force. It's upward, so it's positive, right? Okay, by applying here the second law of Newton, sum of forces equals negative ma. What is the sum of forces? It is Fn in the positive direction, negative mg. What do we care about here? We care about Fn, okay? It is the reading of the scale. So Fn, if you want to get it, so what do you have here? Negative ma. Keep it. You will move this to the other side, right? So it will be plus mg. See, mg is the true weight, okay? So see, I just put mg before. mg, it's positive here, negative ma. So look girls, you are subtracting a number from mg, from the true weight, okay? So here what you are going to feel? You are going to feel lighter. Why? Because here the apparent weight, the reading on the scale, is less than the true weight. And can you girls get the apparent weight? You have to, because you know the true weight is 500, so you put instead of mg 500, and you know the acceleration is 2, and the mass of person is 50, as we said before. So 50 times 200, and the true weight 500. 500 negative or minus 100, it will be 400. So you are going to read 400 on the scale below you, which is less than the true weight, okay? So all of these cases are logic. We experience them in our everyday life, but here we are only, girls, proving them with examples, okay? So when the elevator accelerates downward, always we feel ourselves how? Lighter. And when the elevator accelerates upward, we feel ourselves how? Heavier. But girls, for sure, to feel this feeling, you should use an elevator like for more than 5 floors, okay? Because the slow elevators, if you use slow elevators like for 2 or 3 floors, these slow elevators, they tend to move at constant speed, so no change in the scale reading will be observed, okay? But the measurements will be easier if you use an elevator in a building that has more than 5 floors, okay, to experience this feeling. Now the last and the most important case, the case which explains weightlessness, okay? What is weightlessness now? See, in case you are in the elevator and the elevator cable breaks, oh my god, so the elevator cable breaks, what are the two forces acting on you? Fg and Fn, right? Okay, but when the elevator breaks, that means the elevator here is falling toward the earth, is falling, so is in free fall. So what is the acceleration of the elevator and of you also, because you are inside the elevator? So the acceleration now, it's not 2 or 3 or 4, no, the acceleration now of the elevator and the person system is acceleration due to gravity, because this object is just falling toward the earth. So it's 9.81 meters per second. Okay, let's apply the second law quickly together. What is second law? Sum of Fn is F is equal ma. What is A now? So pay attention. A now is the acceleration due to gravity, because the cable breaks and the elevator is falling. Okay, so force is the same. F negative Fg because down, plus Fn equals negative because downward, m, what? We said this is now g because it's in free fall. Okay, so negative, let's replace Fg in its quantity. It's negative mg plus Fn equals negative mg, right? What do we care about? Fn, it is our reading. So Fn is negative mg, you keep it, and you bring this to the other side, so it becomes what? Plus mg. So see, girls, negative mg plus mg, same quantities, so negative plus, so it's what? 0 Newton. So in this case you are going to feel that you have no weight. You are going to read on the scale 0 Newton. Nothing is supporting you, nothing. So here Fn, it's not present. Fn is 0, and in this case the scale reading is 0. Okay, so this is weightlessness. This is when we feel that we are weightless. Okay, examples of weightlessness. Here some examples. So weightlessness, we can simply say no support force. What is the support force that we mean? No contact force. What is it? It is Fn. No Fn. Okay, because the scale reads Fn, and if there is no Fn, Fn is 0, so no weight. Okay, no weight. This is for sure, we call it apparent weight. It's not the true. In reality we have weight, okay, but we can't feel it. An astronaut is weightless, because he or she is not supported by anything. The body responds as if gravity forces were absent, and this gives the sensation of what? Of weightlessness. Okay, so here pay attention on this note, please. When they say things like the space shuttle has escaped the Earth gravity or has reached a point outside the Earth gravitational pull. So here pay attention, this is wrong. This statement is wrong. Why? Because even though the space shuttle has like moved far away from the Earth, but gravity is still acting on it. Okay, the gravity is still acting. Without this gravity, girls, the space shuttle wouldn't move in an orbit around the Earth. It will go out of the orbit, exactly like satellite. For satellite also, the satellite, okay, without the gravitational force, it will not stay in its orbit. Okay, so it's wrong to say this statement. It's wrong to say it. Always there is gravitational force, because according to the law of universal gravitation, F is equal g m times the mass of the other object divided by the distance squared. So this exists and is not 0, even for huge distances far away from Earth. So only we can say that this gravitational force is 0 when the distance becomes like infinite distance. Some examples about weightlessness: when you are on turbo drop here, or for sure in a spacecraft, inside the spacecraft. Here some examples: daily life inside spacecraft. We know that the astronauts, they stand by fixing their feet in foot restraints, because girls, without these they can't stand. Okay, they will float inside the astronaut, the spacecraft. Why? Because in this case they are in free fall toward the Earth. The spacecraft, including everything inside it, persons and things, is in free fall toward the Earth. Okay, so these astronauts, they feel weightless. Astronauts, they exercise regularly to keep bones and muscles strong. Why? Here, because girls, on the surface of Earth, the gravitational force pulls the blood downward, so that the blood collects in the veins of our legs when we stand. But for astronauts, where girls, the gravitational force has no effect on the body. There is a gravitational force, but it has no effect on the body. Okay, so in this case, this can cause many health problems. Okay, so, and it can cause, for example, nausea, and dizziness. So that's why they make exercise regularly to keep bones and muscles strong. Daily life here, another one. Astronauts also they move like divers under weightless conditions. And even also when they sleep, they fix themselves in beds, avoiding floating around. So for tomorrow we have this section review homework and help you understand the lesson.